Welcome to this lecture session on operational research. So in this lecture session, we are going to discuss about solving problems using Simplex Method. And in the case of linear programming problem, the linear programming problem involves the following steps. Solving a linear programming problem involves the following steps. Initially, the given problem has to be formulated. See, formulation refers to writing the given problem in the mathematical form. So this is what we call as formulation. So generally the problem will be in wordings, so that we have to express in mathematical form. So this we call as formulation of the problem. Once we formulate the problem, the linear programming problem appears like this. So normally we will be having an objective function. This here in this case, this is the objective function. So this objective function will be either to maximize or to minimize. So in our problem that we have considered, it is maximization here. Followed by this objective function, there will be a set of constraints. Basically, these constraints we call it as structured constraints and non-negativity constraints. So any linear programming problem will have these two types of constraints. Constraints are nothing but certain sets of conditions which has to be satisfied to obtain this objective function. The objective function and the set of constraints, they will be made up of decision variables. This x1 and x2 are called decision variables. So in any linear programming problem, the objective function and the constraints are made up of decision variables. Right? Now let us say we are going to solve this problem. To solve a linear programming problem, various methods of solution are either we can solve this using a graphical method or using simplex method. So there are two different methods available to solve a linear programming problem. But this graphical method can be used provided if you are going to have only two decision variables. For the problem that we have considered here, we have two decision variables, and the decision variables are x1 and x2. So this problem can be solved either with graphical method or with simplex method. Now we are going to see how to solve this problem using simplex method. So coming to this simplex method, to solve this problem, we have to express this given problem in standard form. That means here what we are going to do, when I say standard form, we have to express, we want to segregate the variables and constants in the objective function. That means like here you have z, x1 and x2. These are the variables that are available. That is an objective function. Z, x1 and x2 are the decision variables. So all these variables I am going to bring it to the left hand side. And if there is any constant, that I will be expressing in the right hand side. So, and followed by that, in the constraints, we have inequality symbol here. So these inequality symbols has to be replaced and we should have equality symbol here. Moreover, if we have any negative sign in the right hand side of the constraints, that should be made as positive. To make this as positive, how we are doing? We have to multiply it. Let us say if you are going to have instead of plus 60, you are having minus 60 here. And my negative sign is not allowed on the right hand side. So for that, what you have to do, you have to multiply this complete equation, this constraint equation by minus 1. Multiply this by complete equation by minus 1, then this will become positive. And remember, the symbol of the direction of the symbol will change. If this is less than or equal to, then this will become greater than or equal to. And luckily in this problem, they have given positive on the right hand side. So this problem, if you want to express in the standard form, then it will be like this. I am expressing this in the standard form. The given problem has to be immediately written in the standard form. So standard form is like, I am going to separate for the objective function, I am going to bring all the variables together to the left hand side. So maximize z equal to 3x1 plus 5x2, so that will become minus 3x1 minus 5x2 equals 0. Okay? So in the right hand side, we are going to write the constants, and in this problem there is no constant. This is subject to the set of constraints. It is given that first constraint is x1 plus x2 less than or equal to 60. So that will be written like this, x1 plus x2. This inequality has to be replaced by equal symbol. So to replace this inequality into equal symbol, so what we are going to do is that, you see, the left hand side of this constraint equation is less than your right hand side. That means you have to add something to this left hand side. So for this, I am going to introduce a variable called slack variable. So S1, slack variable S1 I am introducing here. This is equal to 60. That means the value of the slack variable S1, either it can be greater than or equal to 0. See, let us say if this is x1 plus x2 is less than 60, that means we are adding s1 whose value is greater than 0. If this x1 plus x2 is equal to 60, then the value of s1 equals to 0. Right? So this variable we call as slack variable. So that we have introduced. This is introduced in order to make the inequality into equality. So this is for the first constraint. Similarly, we will be writing for the second constraint. Second constraint says x1 is less than or equal to 40. So since you have less than or equal to symbol, again I am introducing a slack variable which is s2. This is equal to 40. The subscript that is given for the slack variables like s1, s2, 1 and 2 are the subscript that is given here. The subscript refers to the constraint equation number. So this refers to this s1 refers to your first constraint equation, therefore I have written s1. So for the second constraint equation, the slack variable is s2. Similarly, for the third constraint equation, if you write, then it is x2 plus s3 equals 30. So this is the standard form of the given problem, and for this case you have to write the non-negativity constraint. The non-negativity constraints are x1, x2, these two values of x1 and x2, followed by remaining variables that we have introduced, that is slack variables s1, s2, s3 are all greater than 0. This we call as a standard form. Once you write this in the standard form, then we will be forming the initial simplex table. To form the initial simplex table, what we will do is that we will write the initial simplex table. Initial simplex table appears like this. Initial simplex table. It has basic column followed by Z column, then list down all the variables. How many variables are there? x1, x2, s1, s2 and s3 are there. So we are going to write all the variables here. We are going to list down all the variables followed by the solution column or RHS column. Solution column or RHS column. So we are going to express like this. Right. Now in this simplex table, initial simplex table, I am going to write only the coefficients of the variables. So initially let me start with the objective function. So this row we call it as objective function row. Very first row is objective function row. So and followed by the write the basic variables for each and every constraint. For each and every constraint equation, we have to express one variable as the basic variable. So when you have here we have slack variable. If you have slack variable, then we will be considering slack variable as the basic variable initially. Then subsequently when we iterate, then the slack variable may leave the basic one. And if you are in some cases what will happen, you will be having both slack variable and artificial variable. When you have a slack variable and artificial variable, then we will be considering the artificial variable. The discussion about artificial variable we will be discussing when we discuss about two-phase method. Right now in this regular simplex method, we will have to dealing with artificial variable. We will be having only the slack variable. So we will be writing in the basic column the slack variables for every constraint equation. So we have three constraint equations. So I am expressing the slack variables in the basic column. So let me write the objective function row, very first row. I am going to write only the coefficients. Coefficient of z is 1 in the objective function, and coefficient of x1 is -3. Coefficient of x2 is -5. Coefficient of s1, s2, s3 are 0 in the objective function. Then followed by solution column is also 0 in the RHS. Then coming to the first constraint equation, this is the first constraint equation. I am going to write the coefficients here. We don't have z, so this is 0. Then coefficient of x1 is 1, coefficient of x2 is 1, coefficient of x1 is 1, coefficient of x2 is 0, s3 is 0. Solution column is 60. RHS column is 60. For the second constraint equation, coefficient of z, we don't have any z here, so coefficient of z is 0 and x1 is 1 and there is no variable x2 here, so this is 0, coefficient of x2 is 0, coefficient of s1 is also 0, coefficient of s2 is 1, coefficient of s3 is 0 and in the RHS we have 40. Coming to the third constraint equation, for the third constraint equation there is no z here and there is no x1 also, coefficients are 0 for z and x1, coefficient of x2 is 1, coefficient of s1 is 0, s2 is 0, s3 is 1, then right hand side is 30. So this is the initial simplex table. So this we have to form. Then to apply simplex, before we apply simplex, what we have to do is that we have to check, we have to make note of this, we have to check these two, like in the objective function row, corresponding to the basic variables, zero should be there. This is the first check. And also, corresponding to the basic variable, you should have unit matrix. There should be unit matrix corresponding to basic variables in the initial simplex table. This is the check. Okay. I'll show you now. So your basic variables are s1, s2 and s3. Corresponding to s1 we have 0 in the objective function row. In the objective function row we are corresponding to s1, s2, s3, 0, 0, 0 are there. And you should have unit matrix in the initial simplex table corresponding to the basic variables s1, s2 and s3. This is 1, 0, sorry, s1, s2, s3. So this is this. You should have unit matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So these checks has to be done. Then after making sure that you have the unit matrix and zeros corresponding to the objective function row, then we will go to the problem. We will apply syntax. So to apply syntax, what we have to do is that we have to determine the entering variable. Next step is that we have to determine the entering variable. So how to determine the entering variable? So this is determined like this. If the problem is of maximization type, then it is determined like this. For a maximization problem, we will determine the entering variable as the variable having most negative coefficient enters. Variable having most negative coefficient in the objective function row. Enters this coefficient. And for the problem is of minimization type, then the variable having most positive coefficient in the objective function row enters. So our problem is of maximization type. So the variable having most positive coefficient in the objective function row enters. So to determine the entering variable, so in this is the objective function row. In the objective function row, each variable is having most positive coefficient that we are checking. And we have identified that variable x2 is having most negative coefficient. So this variable x2 is going to enter. So this is the entering variable. So we have identified the entering variable. So now we have to determine the leaving variable. So to determine the leaving variable, procedure is same for both maximization problem as well as for minimization problem. To find out the leaving variable, this is common for both for maximization as well as minimization problem. This is minimum of solution column or RHS column or entering column greater than 0. Entering column greater than 0. So this is how we determine the leaving variable. So to determine the leaving variable here, you see the simplex table is determined like this. I am not determining leaving variable. So here in this is the entering column and this is the solution column. This is entering column and this is solution column. So solution column divided by entering column greater than 0. This is 60 divided by 1. For this, 40 divided by should be greater than 0. 40 divided by 0. But this value of the entering column should be greater than 0. But since this is 0, I am not going to consider this. Coming to the third case, for this it is 30 divided by 1. 30 divided by 1. So among these three, so this is having at the denominator 0, that's why we are not going to consider. Among these two, which is minimum, so this is the minimum value. So therefore, this variable S3 is going to be, so this is the leaving variable. This is the entering variable. Entering variable is x2, leaving variable is S3. So this column is called entering column. This complete column is called entering column, and this row, complete row is called leaving row. So this is leaving row, and this is entering column. The intersection of this entering column and leaving row, this element we call it as pivot element. This we call it as pivot element or key element. So this we have to identify, because in the very next iteration we have to make this value as 1, and fortunately in this problem we have this value as 1. Otherwise, let us say if you are going to have 4 as the pivot element, then in the very next iteration you have to make that value as 1. How will you make this? To make this value, let us say if it is 4, and if you want to make it as 1, this is an equation. So you have to divide this complete equation throughout by 4. Then you will get 1. And fortunately in this problem we have 1. So therefore directly I am going to write this. So in the next table, there is going to be like this. Next table. So this is our initial table. So we are going to proceed further. So to proceed further, is like this. This is the basic column. The basic column I am expressing S1 will remain same, S2 will remain same, S3 is leaving. S3 is leaving, and what is entering? X2 is entering. Therefore, instead of S3, I will write X2, because X2 is the entering variable and S3 is the leaving variable. And now this pivot element should be made as 1, and luckily we have 1. So let me write as such. There will not be any change. Now the next step is that this is pivot element. This we have made it as 1 here. Above and below this pivot element, I should have 0. Right? We have to make this as 0. How to make this as 0? Now let us say we take the objective function row. This value should become 0 here. To make this as 0, what we are going to do is that we are going to multiply this by 5 plus 5. So multiply this by plus 5. Add to this, right here, we will get 0. That means I am going to use 5 x2 row of the first iteration. I am going to add this to the objective function row of the 0th iteration. I am going to write this in the first iteration. I am going to multiply this x2 row of the first iteration with 5 plus 5, and I am going to add to the corresponding value in the objective function row of the previous iteration, and I am going to write it in the present iteration. So I am going to multiply this by 5, add to this, write it here throughout this equation. Multiply this by 5, add to this, multiply this by 5, you will get 5 into 0 is 0, 0 plus 1 is 1. Multiply this by 5, you will get 0, then add to this, you get minus 3. Multiply this by 5, add to this, you get 0. Multiply this by 5, add to this, 0. Multiply this by 5, add to this, again 0. Multiply this by 5, add to this. 5 into 1 is 5, plus 0 is 5. Multiply this by 5, you get 150, plus 0 is 150. This is for the objective function row in the next iteration. Coming to the S1 row in the first iteration. This is the first iteration. Coming to the S1 row, so this we have to make it as 0. In the previous iteration we have 1. How to make this as 0? For that, this x2 row I'm going to multiply by minus 1, add to this and write it here. That means I'm going to multiply this by minus 1, this present x2 row of the first iteration, and I'm going to add to the s1 row of the previous iteration, and I'm going to write it in the s1 row of the next iteration. Right? I'm going to multiply the x2 row of the present iteration with minus 1, and I'm going to add that to the values in the s1 row of the previous iteration and write it in the s1 row of the present iteration. Okay. So multiply this by minus 1, add to this, write it here. Multiply this by minus 1, add to this, write it here. Multiply this by minus 1, you get minus 1, you get 0, plus 1 is 1. Multiply this by minus 1, add to this, 0. Multiply this by minus 1, add to this, you get 1. Multiply this by minus 1, you get 0, plus 0 is 0. Multiply this by minus 1, you get minus 1, add to this, you get minus 1. Multiply this by minus 1, add to this, when you multiply this by minus 1, you get minus 30, plus 60 is. Coming to S1, coming to S2, this we have to make it as 0, and luckily we have 0 here. So we are going to write this complete coefficients directly from the previous iteration because already it is 0 here. This is the first iteration. And when you perform simplex, you have to check for optimality. We say like the solution is optimum provided when all the entries in the objective function row are greater than or equal to 0, then optimality is reached. This we infer, this is how we check whether we obtain optimality or not, and this is for the maximization problem. The problem is of minimization type. Then when all the entries in the objective function row should be less than or equal to 0, then we say that optimality is. Our problem is of maximization type. So therefore, when all the entries in the objective function row are greater than or equal to 0, then we say that optimality is reached. Now we can check. This is the objective function row. So in this iteration, in the objective function row, do we have all entries greater than 0? No, we don't have. So this is negative value. So that means objective function is, the optimality is not reached. That means we have to iterate further. To iterate further, what we have to do? Once again, we have to apply simplex. The step involved is like you have to find out the entering variable. How will you find out the entering variable? For maximization problem, entering variable is like the variable which has most negative coefficient in the objective function row that vectors. So which is having the most negative coefficient in this? Minus 3 is the most negative value. This is corresponding to variable x1. So variable x1 is going to enter. Again, we are going to do the integration. So this is the entering variable now. X1 is going to enter. So now we have to determine the leaving variable. How will we determine the leaving variable? To determine the leaving variable, so procedure is minimum of solution column divided by entering column greater than 0. This is for the first case. Yeah. So to determine the exit variable, to determine the entry variable and exit variable, entry variable we have determined for the most negative value in the objective function. The corresponding variable is x1. So x1 is the entry variable, and we are going to determine the leaving variable. To determine the leaving variable, just like entering column, solution column divided by entering column greater than 0. So this is 30 by 1, and for this 40 by 1. Here we will not have plus denominator is 0. So among this is last value. So the leaving variable is s1. Leaving variable is s1 now, and this is entering column. And this is the leaving row. So this intersection that we have this pivot element. So this pivot element we have to give it as 0 in the very next iteration. Before that, we have to check whether we have obtained optimality or not. So we didn't reach the optimality, so we are going for the next iteration. So in the next iteration, so the basic variables are s1. S1 is leaving. So instead of S1, X1 is going to come in. So entering variable is S1, and other basic variables are S2 and X2. Now, this variable, this value we have to make it as 1, and luckily in this iteration also we have 1. So we will write directly here 0, 1. 0, 0, minus 1 and 30. And the values above this and below this should be 0. So that we have to make it as 0. Let us say for the objective function here, I want to make it as 0 into x equation. So for that, what we have to do? We have to multiply this x1 by plus 3, then add to this, make it 0. So what I am going to do is that I am going to add x1 with the set of the previous iteration. Let us say first iteration, this is second iteration. This I am going to write it in the objective function row of the second iteration. So I am going to multiply this by plus 3, add to this right here. So if you multiply this by 3, you get 0, 0 plus 1 is 1. Multiply this by 3, add to this, you get 0, multiply this by 3, plus 0 is 0, multiply this by 3, you get 3, 3 plus 0 plus 3. Multiply this by 3, add to this, 0, multiply this by 3, add to this, you get 2. Multiply this by 3, you get 90, add to this, you get 240. Now, we have to make this as 0. To make this as 0, we have to multiply this by minus 1, then multiply this by minus 1, add to this. So for that, this is minus x1 of the second equation plus s2 of the previous equation. We are going to write it as s2 of the second equation. So for that, we are going to multiply this by minus 1, add to this right here. Multiply this by minus 1, add to this right here. Multiply this by minus 1, add to this right here. Multiply this by minus 1, add to this right here. Multiply this by minus 1, add to this. Get minus 1. Multiply this by minus 1 is minus 1 plus 0 is minus 1. Multiply this by minus 1, add to this. Multiply this by minus 1, you get plus 1 plus 0 is plus 1. Multiply this by minus 1, add to this, you get 10. This is for the S2 row. Coming to the X2 row, here this you want to make it as 0, and luckily in this case we have 0 equals to 1 right directly. Values 0, 0, 1 and 30. Now you check this table, right? All the entries in this objective function row are positive. If you have all entries in the objective function row as positive, that means we have reached optimality. Now the entries in the objective function row are positive, are greater than or equal to 0. This means we have reached optimality. This is the optimum basic feasible solution. Because since all entries in the objective function row are greater than or equal to 0. Therefore, optimality is reached. Also, we have to check corresponding to the basic variables. In the objective function row, you should have 0. It should be there in all iterations. And you should check for unit matrix. Let us take the case of the first iteration. In the case of first iteration, basic variables are S1, S2, and X2. Corresponding to the basic variables, corresponding to S1 in the objective function row, we have 0. Corresponding to S2 also we have 0. Corresponding to X2 also we have 0. And you will check for unit matrix. For S1 it is 1, 0, 0. S2 0, 1, 0. For X2 it is 0, 0, 1. So we have unit matrix. And in the second iteration also, if we check for this, basic variables are x1, s2, x2. Corresponding to x1, we have 0. Corresponding to s2, we have 0. Corresponding to x2 also we have 0. And for unit matrix, 1, 0, 0, 0, 1, 0, 0, 0. So this we have to check in each and every iteration. This indicates that we are proceeding in the right direction. If there is some mistake, that is your practice is some mistake. So after this is the final result. So the final result says, from this I can write the final result. This like the final answer is maximum of z value is equal to 240 and the decimal variables values are x1 value plus 30